Okay, we've got 8:30. Why don't we get started? Good morning, everybody.
Good morning.
Welcome to Wednesday of week number 5. What I thought I'd do first is just start us out with an overview of where we're going to be going for the next several class sessions so that we can see the big picture and then we'll start to zoom in. So here we are on the last day of September, and we're going to be talking about linear and nonlinear regression most of today, and we're going to be building toward next week, where we have an exam and a computer quiz, our typical pair, and those come up every couple of weeks, as you can see here. The computer quiz will be in class. The exam will be a take-home exam. Like always, it will be a written exam, and you'll have the opportunity to write about many of the concepts that we've been discussing. So it's a chance for you to integrate. I'm looking forward to that. I'll hand that to you, that prompt to you on Friday, so that you'll have a full week to do that, okay? And as we get closer to the computer quiz, we'll talk more and more about the kinds of things that we would be computing on that quiz. Certainly there will be some correlation. We did some manual computation of correlation, and we'll do some more of that tomorrow, okay? We'll also be talking about effect size on that Monday, or obviously that Wednesday, and we'll talk a little bit about effect size on Friday. Okay, so to back it up to more current times, we could say that we had a really good conversation on Monday. We had a good conversation about the journal article, but we also had a really nice introduction to causal modeling from Gwen. She gave us this, okay, and she told us about the causal relationships that were inferred here through the causal modeling process. And we had a TED Ed that I'd like to go over this morning on causal modeling. We didn't get to go over the TED Ed previously, so we'll make sure that we have a moment or two to do that. I also wanted to check in to make sure that we had our next couple of presenters, and I think we have Shelby coming up on Monday, is that right? And I think the Monday after that we have Victoria, okay? So we'll have presentations from you on those days. Okay, all right, so that was that. And to set up the idea of causal modeling, we were finishing up our conversation on correlation. And one of the last questions that we had on correlation was about the idea of ceiling effects and range restriction. So just a quick show of hands. Who remembers talking about range restriction last time we were together? Okay. Right. So we were having a conversation on range restriction. I guess that was Friday, and we were just about running out of time. But I wonder if somebody can develop that idea for us. We talked about range restriction, ceiling effects, and floor effects, and we had an example about the NFL and weight. Can somebody help us out in just remembering what that example was? Okay, thanks, Hannah.
We said that I think the linebackers' weight wasn't correlated with success.
Okay.
But in the NFL, all of the linebackers' weights are the upper end of the range.
Uh-huh. Okay, right. They're all at the upper end of the range, so they're a restricted portion of the range, a restricted portion of the range. Okay, so that's going to tend to reduce our correlation. Right? There might be a significant correlation between one's body weight and one's success as a linebacker, but if you're dealing with a restricted range, you're not going to see that. Who remembers doing that in that diagram? That all sound familiar? Okay, and so that's generally the case with floor and ceiling effects. You'll find that you typically will have a very restricted range of scores. And then we took a limiting case, the ultimate range restriction, when all of these scores on the y-axis are exactly the same as one another. We do something like this. I'll simply call this y. I'll call this x. And we can have a bunch of different x scores, but all the y's are, in this hypothetical, exactly the same. And we asked about the r value associated with this, or equivalently the r squared. Okay. And we had a couple of different kinds of answers. So what were some of the possibilities that we had here for the value of r, just intuitively? I think I heard somebody say that. What's a possible r value there? Undefined, okay? Undefined is the actual answer, right? And what's interesting about that is typically when every dot is right on the line, we have a very, very high r. So r might be something like 1, or if it were negatively sloped, it would be -1, and then we square that and we wind up with 1. Okay? Another way of thinking about that is that the slope of that line sometimes tells us about whether we have a correlation or not. And we can think about the slope of that line being proportional to the r value itself. Okay? So this would be a really, really flat slope, so you'd say, well, that's probably an r value of 0. So intuitively, you might say, well, the r value here is 0 because the slope is flat. You might say the r value is 1 because every point is right on the line. Okay? So on some level, 1 is a plausible number, and 0 is a plausible number. So that should tip us off that it can't really be 0 and 1 simultaneously, given that we want this to be either 1 or the other, and the r squared goes from 0 to positive 1. Right? So a given data set with its best fitting line can't be both 0 and 1, the two extremes there. And so that's undefined. And just to remind you, we kind of ran out of time on this, the R equation is SP, xy, over the square root of SSX times SSY. You don't have to memorize that, but the idea would be that if we look at all these y scores, let's just say that this was a 4. I don't think I made it 4 the last time, but this particular score is a 4. That's a 4, that's a 4, that's a 4, and that's a 4. What's an average of all those 4s? 4? Okay, okay, right? And the standard deviation? 0, okay? The standard deviation is 0. Let's think about, how about the sums of squares? Okay. So remember, we got the sums of squares by saying that we have, here's a list of scores, they're all 4, okay? Then we get the deviates, and we do score minus mean, okay? So what was the mean again of this group? 4, okay? What's 4 minus 4? 0, okay? If we add up a whole list of zeros, what would a whole list of zeros add up to? 0. But now you square it, okay? And so SSY in this case turns out to be 0. Who's okay with that? And when we multiply 0 by any number, we get 0. And then we can take the square root of 0, and we get 0. Now we have 0 in our denominator, and we remember from maybe 4th grade or so, that's undefined. Okay? So that's where that originates from. If all these scores are the same, there's no deviation. The square deviations are also 0. And this whole thing now comes back down to undefined. Okay? So in an ultimately restricted range of y scores, it would be undefined. But more generally what happens is when you restrict the range, it doesn't go all the way to 0, but you get r values that are closer and closer to 0. Right? You need some variability in order to have a significant r. Okay? So that was how we were wrapping up our conversation on correlation. And then the next thing that we did was we had a TED Ed on causal modeling. And really appreciate that Gwen had picked a article that was not only topically interesting to her, but it had that causal model that we had seen. So I thought we'd go through at least some of the questions from TED Ed on causal modeling. So this was for Friday's class, and we'll do just a few of those, and then we'll make our way into today's TED Ed for regression. And then we'll also do some hands-on exercises today in regression. But we won't do any heavy computation in regression. We'll save that for tomorrow. By the way, for tomorrow you will not have another TED Ed, so you kind of get the night off. I know you have a lot of TED Ed questions, and you're doing lots of other things, so we'll give you a night off tonight. We'll come back in tomorrow, we'll do some hands-on computations. I'll hand you a couple of formula sheets. We'll make our way through some Excel computations. We'll also do those in SPSS. Today we'll play around in Excel, but we'll have Excel do the computation for us. But before we do the computation, let's get the conceptions down. And a lot of the regression work finds its way into causal modeling. So the very first TED Ed question that we had on causal modeling was, in your own words, briefly explain what a causal model, or what causal modeling is. Anybody want to put some words around that? Causal modeling. Maybe this will help. Maybe it won't help. We'll find out. So, okay. Hopefully people can see that. This is a pretty prototypical causal modeling approach. And we saw glimpses of this in Gwen's presentation the other day. Thanks.
The causal model is making a graphical representation of a system's correlational mechanism.
Okay.
Usually in a diagram.
Okay. Really good, okay. Causal model is making a graph of the system's correlational mechanisms. Now that's interesting, right? Because we always say in Psych 100 that correlation does not imply causation, but we are going to show the correlations here. And this would be the simplest kind of a case. We would begin in Psych 100 with a relationship between these two variables. Now we introduce a third variable, and we get a correlation coefficient for all of those, right? So we can do, if this were in Excel or if this were in SPSS, we would have a list of numbers associated with this variable, a list of numbers for that variable, a list of numbers for that variable. We can find all the pairwise correlations, right? A to C, with path A, path B, and path C here. And we get simple equals Carrel or equals Pearson for each of those. Okay? All right, so that's the idea. And what else can we say about that? So we now have these correlations. Right? We're trying to draw a causal inference. Okay? I'm kind of moving on to question 6 here. I don't know if I want to go just that far yet to question 6. But the idea in question 6 was to figure out what do we do with those correlations when we're asking the question about establishing mediation. So frequently the phrases that you'll hear when you're talking about causal modeling, you'll hear about mediators and moderators. Okay? Let's see if we can understand a little bit about these correlations that Gabby has just introduced and mediational analyses. Okay? So anybody want to take us through the steps associated with maybe establishing a mediator, a mediational analysis? Thanks.
First, you want to establish the independent variable influences the dependent variable.
Okay, or at least it's correlated with. Okay, if I can just pick up. So influences was a reasonable word to use, but it almost suggests causation, and it might be, but at least it's correlated. Okay, so we'll go just that far. So we establish a significant relationship here, okay?
You also want to check that the independent variable correlates with the mediating variable.
Okay, so we do that equals Carrel, this guy and that guy. We come up with another R and see if that's significant, okay?
And then finally, that the mediating variable correlates with the dependent variable while controlling for that first independent.
Okay, right. So the first step is just to get a correlation on all of those, and we hope all of those are significant. Then you might even see it this way sometimes. You might get a fourth correlation. Okay? What you might do is get these three, and then you'll get them just straight up. This one with that one, this one with that one, this one with that one. Just straight pairwise correlations. Then what happens to this primary correlation, that's the one of interest, right, after having controlled for and removed the influence of the mediator? Okay? Now, if you can factor out the mediator somehow, and then having factored it out, take a new correlation between this one and this one, we typically like to see, has there been a reduction, a statistically significant reduction in the strength of this relationship? So sometimes along this bottom arrow, you might see two correlations listed. What was the initial correlation, right, just straight up, and then what was the second correlation after we had removed the effect of the mediator variable? Who's following that? Does that work for us? Okay. And how you remove that is a matter of some computation that we might get into later this semester. But you'll see two of them there. And ideally, if that were a really, really strong mediator, that correlation would go absolutely to zero. It wouldn't go to undefined, typically, but it would go to zero. In a more typically observed case, it won't go all the way to zero, but it will be significantly reduced. Okay? So it's a significant reduction in what was otherwise a significant correlation initially. Okay. Now, when you get that significant reduction, it might be the case that you're pretty close to zero, and this is not exactly zero, but it's now non-significant. It might be that it remains significant, but it still is significantly reduced. Okay? So who's following all that? Okay. Okay. So a simple example. It's one possibility. And I hope you'll forgive the simplicity of this possibility, but why don't we go with it, just so that I think it's always easy to keep this one in mind. Okay? So we're going to have 3 boxes, and we might say something like, this is the murder rate in a particular city. Okay? Some psychologists are interested in that kind of behavior, so the murder rate. And over here, it turns out that murder rates for different cities are pretty well predicted by the number of traffic lights in a city. I don't know if you knew that or not, but there actually is a statistically significant correlation between traffic lights in a city and the murder rate. Okay. So we can come up with some kind of an R value there. You can take, the 1,000 randomly selected cities in the U.S., including some big ones, some medium-sized ones, and so forth, and we get this. By the way, who finds that plausible? That I shouldn't say murder rate, I should say number of murders would actually be better. Right? Murder rate probably isn't that, but I'm going to say number of murders. It's correlated with the number of traffic lights. Okay. All right. So what do you think? Why don't we just get rid of the traffic lights and we're done, right? Shelby's making a funny face. Okay, we need a mediator. What might be a mediator over here? Thanks, Karen.
Population of the city.
The population of the city, okay. see if that might make sense. So the first move was to go from here to here. I think they call that path A over, okay? Do we think there's going to be a significant correlation between the number of traffic lights in the city and the population of the city? Bigger cities, other things equal, ceteris paribus, tend to have more traffic lights. Yeah, that works, okay? Bigger cities tend to have a greater number of murders per unit time. And we call that C, we'll call that B. Okay. And then here's, we already knew this one was correlated, and then we can have C1, comma C2. So these two correlations, before and after, have been controlled for that. Okay? So you can see, just in this simple example, why you'd want to factor out the population of the city before you're going to try to draw a conclusion about whether there was a causal relationship between this and this. You'd want to factor that out. Okay? So real easy model to think about. And if we always stay with that, then as our models get more and more complicated, this will, I think, be a good guidepost for us. Okay? All right. Who's all right with that? Okay, it looks like all hands are up. Okay, I think people are okay with that. So now we've talked about the idea of getting a system filled with correlations and trying to figure out maybe what's causing what. And we have this mediational test where we find all the correlations, and then we factor out the mediator variable, and we see what happens to this initial relationship. Okay, that's about mediation. We're trying to get to cause. The other major term that we have when we talk about causal modeling is moderator. Okay, so can somebody help us out with that? And I can give you the question number if it helps you. This was questions 8 and 9. In your own words, briefly explain what a moderator variable is, and then might you be able to generate an example. Well, let's just see if we understand what a moderator variable is. It was question 8 and 9 on Friday's TED Ed, which would have been called causal modeling. Okay, thanks, Anna.
A moderator tells us what the conditions that affect the strength or direction of a correlation. Okay, really good. Yeah, we'll use those two words, the strength and the direction of the correlation, right? So it might be the case that this moderator variable, this could be mediating, it could be moderating. It still might be the case that we have a significant relationship, but this thing somehow reverses the direction of that relationship, or it reverses the strength of that relationship. And one of the ways of thinking about the moderator is that it's very much like having an interaction in a factorial design that you learned about in research methods. So we do, in research methods, talk about simple bivariate analyses, and then we have one variable to be predicted by many different kinds of predictor variables, and we call that a factorial design. And it might be the case that one of those variables is interacting with another one of those variables. So we can think of the moderator very much as a interaction effect. And we'll be having a conversation about those. Did anybody come up with any moderator variables? So generate a novel example of two variables that might plausibly be moderated by a third variable. Anybody want to start us off with that? It's hard to generate novel examples, but if you can do it, it suggests some level of mastery with that concept. It might be helpful to think about a simple 2x2 graph. So two variables, or one variable that has two levels here, and then maybe it's plotted in two different colors, red and blue. Right? So the first level of that variable is in red, the second level of that other variable is in blue. Okay. Who remembers what a interaction might look like on a graph? Evidence for an interaction? We're looking at a 2x2 graph, and we're asking ourselves, gee, how do we know if we have an interaction there? There's usually a quick visual test that you can do. You probably learned it in research methods. I actually do it even in intro, but not all of us have professors who do that in intro. What do we look for in a 2x2 if we're trying to find out whether there's an interaction? Does anybody recall? Okay, thanks. The lines cross.
The lines cross, okay? So it might be the case that on the first level of the x variable, the blue is higher than the red, and then on the next you get the reverse pattern. If you connect the blues and the reds, you get a crisscrossing pattern, okay? So we get one direction at one level, and then the opposite direction. So we're changing now the direction of that relationship by having a moderator variable. Just to give you one possible example, my PSYC 341 group I might be able to call it up really quickly, is doing an exercise now on mindfulness. So let's see if I can call that up. And they have something that's approaching an interaction. So let's see if we can go to Project 1 Materials. Here are their data. And they're doing a particular kind of cognitive test. You may have used CogLab in some of your Intro to Psych laboratory exercises. And they're making some kind of a cognitive test where we're following the proportion correct, and we're seeing how correct people are and also how fast they are when they're doing this test. And half of the people are in a simple control condition. The other half have gone through a mindfulness exercise. Okay? And there's two conditions here in our CogLab exercise. One of them is fairly demanding attentionally. It's called the flicker condition. It's fairly demanding. The other one is really, really quite simple. It's the no flicker condition. So this is hard and this is easy. Is one of the ways of thinking about that. And you can see that on the very easy task, these two are almost exactly the same as each other. Okay? But on the harder task that has this flicker in it, it's more attentionally demanding, it turns out that the mindfulness folks have a much lower score in reaction time than do the control condition. Okay? The folks in the control condition. So we're getting something of a difference there, but that difference tends to go away there. You might say then that mindfulness is moderating that relationship. Okay? We actually do get a difference, but it's only appearing here, it's not appearing over here. Okay? So that's one of the ways of thinking about this. And we'll spend a lot of time talking about interactions in the weeks to come, but not this week and not next week. We'll do it after that. I think we get back to that after we do multiple regression. Okay, one last conversation on the causal modeling. And I was really interested in your response to question number 14. In your own words, briefly explain what a latent variable is. I think this is a fascinating idea, the latent variable. And maybe you can give an example of a latent variable. People sometimes use causal modeling to investigate these latent variables. They also use such things as factor analysis and cluster analysis. Okay, Melanie's got something.
So what I got from this was that it was like a variable that in and of itself is unmeasured, but it's kind of assumed that this variable is the cause, like the underlying cause of many of the other variables that are used in the experiment. So what I came up with was like sort of like the overarching variable of quality of life as measured by like socioeconomic status or like.
Wow, that's wonderful.
I don't know.
Let's stay with that. That's a wonderful example. Quality of life. Oops, that guy is not working for us. Quality of life, and your first measured variable was which one?
Like socioeconomic status.
Okay. Certainly there's a covariate. Oh, wow. Do I have a graph to show you? I hope you have a chance. Okay. SES. If we have time, I really want to come back. There's a wonderful graph on quality of life in SES that came out this summer. That was dynamite. Let's help Melanie out. She's on. So this is the abstraction. There's this idea about quality of life. Okay? And what we're really good at in psychology is operationalizing, stating the operations that we would use to get to this abstraction. We all would like to believe that we're concerned about quality of life and improving it around the world. SES is one factor. What else might be another indicator? A measurable indicator of quality of life. So SES is measurable. Okay? What else might be? Is that it? If you're wealthy, you got a high home. What else might it be? Yeah.
Maybe like access to healthcare.
Access to healthcare, okay? Okay, and we can measure that a few different ways. We can say, first of all, do you or do you not have medical insurance? What level of medical insurance do you have? Do you have dental? Do you have vision? Okay, so we can break that down into lots of different measured variables. But certainly access to healthcare, SES. Yeah, thanks.
Maybe number of vacations you go on.
Okay, number of vacations, right? Okay, number of vacations, and we can just go on, right, about all of this. You can say something like, well, one idea is maybe even longevity, right? It was shocking numbers. There's one or two nations in Africa, and their median age is way, way low. It's like 17 or 18 is their median age, and I think the median longevity is like 30s or something. It's way different from ours, okay? That might be one indicator. You might choose to operationalize as quality of life. So this is the abstraction. This is the latent variable. And we can figure out to what extent different measured variables are contributing and to what proportion of contributions these are making. And we can come up with something like an R squared. We can take the R value, we can square it, and get the coefficient of determination. Who remembers hearing that one? Coefficient of determination. And we could say that this variable is playing a big role in predicting quality of life, or it's not playing a very big role. Okay, so latent variables will be coming on board and off again and on again many times throughout the semester. Okay, that was our little conceptual introduction to causal modeling. We didn't do any computation there. Okay, we kept at a relatively low level on Bloom's taxonomy, and we just tried to understand some ideas about these big triangles. Right? We're going to try to use only correlations, but from these correlations, can we get to causation, or at least a better approximation of causation? We introduced mediator variables, moderator variables. Some of those variables could be directly measured, or they could be latent variables. And sometimes it's latent variables that are of greatest interest to psychologists and other scientists. Okay, in order to do that, we need to begin to, in order to really flesh that stuff out, we need to begin to move from correlation to regression, and there is a intimate relationship between those two. So why don't we now go to the TED Ed that we had for today, the TED Ed on regression, and we'll do most of these questions. So this might be fresher in your mind, because you were doing these for today. So why don't we just start out with a simple description? Can somebody explain or even describe what regression is within the context of statistics? What is regression? Here's a hint. We have linear and nonlinear regression, so maybe that tells you what regression is. Anybody want to offer a synonym for regression? Prediction. Okay, thanks. So we're going to be predicting. And usually in order to predict, we would need something, in many cases, more than an R value. Sometimes an R value is enough to do prediction for us, but we might need a full equation. And in the simple linear case, we can use a y equals mx plus b, or a linear equation, to make our prediction. We're going to take in one variable and try to make a prediction about maybe quality of life on the basis of number of vacations, whatever the predictors might be. Okay? So I think we all now have understood question 2 in the context of regression, the difference between the criterion variable and the predictor variable. Right? So the criterion is what we're trying to predict. That's on the y-axis typically, which we also call the ordinate. And then on the abscissa, or the x-axis, we have at least one predictor variable. And when we come back from our exams next week, we'll start on multiple regression. We'll have multiple predictors. Okay? Can somebody explain in their own words the terms regression coefficient and regression constant? We'll stay in the simple linear case, regression coefficient and regression constant.